Hello guys, welcome back to another video. So today I want to talk about a very interesting concept. So a lot of times, let's say if you're in a lab running some experiments or something like that, you might have seen that a lot of times for finding the variance of your observations, you are asked to divide your sum of squared errors with n minus 1, where n is the number of observations instead of n, while in the proper definition for variance, it is the mean squared errors. So why do we remove 1 from n? Where does the n minus 1 come from and not n? And why is n minus 1 used in such cases? Well, in this video, we're going to go through why and where we get n minus 1. And let's get into it. Alright, so let's look into it. Let's look at what we mean by unbiased estimators. So let's say we have a sample x which is drawn from a distribution f with some parameters theta, right? And let's say we have a statistic t of x squared, or the draws from the distribution f theta. Let's say we have n of them. Let's say we draw n samples. So x squared would basically just be x1 to xn. Okay, let's say we have a statistic t x squared, and we say that a statistic t of x squared is unbiased for a parameter, say theta, if expectation of t of x squared is equal to theta. Now, how do we look at an example? So let's say that the statistic t of x squared is just the mean of x, which is basically sum of from i equal to 1 to n of xi divided by n. And if the expectation value of this 1 by n summation xi is equal to theta, then we can say that the mean of the sample is an unbiased estimator for theta. Now let's say the mean of the estimation, let's say the actual expectation is theta plus 1, then this sample this statistic is not unbiased, or is biased towards theta, or even theta squared for that matter. Okay, now let's fix a distribution. So let's say we have the sample xi from 1 to n drawn from normal mu comma sigma square. So we have a normal distribution centered at mu with a variance sigma square. Now mu is basically defined as the expectation value of xi, where I goes from 1 to n, or also expectation of x bar is equal to mu, which is basically equal to expectation of 1 by n summation xi is equal to mu. And now from the definitions of how variance is taught, expectation of 1 by n summation xi minus mu whole square is equal to sigma square from I equal to 1 to n. Now this is the definition which is taught for variances. So why do we not use this in a lot of cases? And where is this flawed? Well, a lot of times, let's say you're given a sample from x1 to xn, but here you use the value of x bar to estimate mu. Now, and eventually what you do is you take the sample variance, which is xi minus x bar whole square. Now this need not be equal to sigma square. The difference is that mu is a constant, and over there, in that case, let's say we know mu, but most of the times we don't know the distribution, so we don't know the value of mu and we estimate it. Now xi's are all random variables, so x bar is also a random variable. Now an interesting thing is that if xi's are uniformly drawn from normal mu comma sigma square, x bar is also a random variable drawn from a normal distribution centered at mu with variance of sigma squared by n. Okay. Now, well, this is basically the central limit theorem. Okay, so now we have a distribution for x bar, which is a random variable, unlike mu, which is a constant, a scalar quantity. So now the same definition need not apply. Now let's see what this expectation actually is, whether it's equal to sigma square or something else. So, well, let's look at expectation of summation I equal to 1 to n xi minus x bar whole square. Now since xi's are independently drawn and identically drawn, that's important, these are independently and identically drawn. So, well, we can see that since expectations and summations are interchangeable, we can just write summation I equal to 1 to n of expectation xi minus x bar whole square. Okay, so now let's just look for any random xi. Okay, so let's just ignore this for now. Okay, so how do we expand this? So that would be expectation of xi square minus 2x bar xi plus x bar whole square. Okay, now since the definition of a variance is basically defined as expectation, variance of x is defined as the expectation of x square minus expectation of x whole square. So expectation of x square is equal to variance of x plus expectation of x whole square. Okay, this is important because now we can write this expectation as expectation of xi square, which is equal to variance of xi, which is sigma square plus mu square for expectation of x whole square, plus sigma square by n plus mu square, because x bar is drawn from normal centered at mu with variance sigma square by n, minus 2 times expectation of xi times x bar. Now you can't separate it out by saying expectation of xy is equal to expectation of x into expectation of y, because over here xi and x bar are clearly not independent, because, well, x bar contains a term of xi in its attainment probably. Anyways, so now this is a quantity which is in our focus right now. What is this value? Well, let's split it up, because we know x bar in terms of xi and other independent quantities, which is important. So that's basically expectation 1 by n into summation xi xj j equal to 1 to n. Now, yeah, so I guess you can see where this comes from, because x bar is equal to 1 by n summation j equal to 1 to n of xj into xi. Now this is 1 by n into, now we have n minus 1 quantities which are independent of xi. So that's n minus 1 into expectation of xi into xj, where j is not equal to I. So that's expectation of xi into expectation of xj, which is equal to mu square, plus one of those terms is expectation of xi square, which is, like we've talked before, mu square plus sigma square. Now this basically comes out to become, this will become mu square plus sigma square by n. Now our final value comes out to be sigma square plus mu square plus sigma square by n plus mu square, oh god, minus 2 times mu square plus sigma square by n. Now you can see where this is going. Our mu squares cancel out and we are left with sigma square into 1 minus 1 by n. Okay, now this is just the value of expectation of xi minus x bar whole square. We need to sum it up n times, and these are all independent, and these are all of this value quantity is independent of I. So we get expectation of the final summation is equal to sigma square n minus 1. So we finally get expectation of 1 by n minus 1 summation I equal to 1 to n of xi minus x bar whole square is equal to sigma square. So finally, our unbiased estimate of a sigma square is 1 by n minus 1 into summation xi minus x bar whole square. Now, why do, if this is the unbiased estimator, why do we even use 1 by n when you're sampling, if you have a random sample? Well, that is because I think I've talked about MLEs before with you guys, and the MLE estimator of sigma square uses 1 by n. So, if you want to get an unbiased estimator of your sample, you need to use 1 by n minus 1. And if you want a maximum likelihood estimator of a sample, you're supposed to use 1 by n for your estimates for the variances. And that is a key distinction between what kind of sample variance you guys need to get in whatever result you're trying to get. And that's an important distinction. So yeah, so I really hope you enjoyed this video, and I hope you like, share, subscribe to my channel, this video, and comment on it, and enjoy life.